the first question is, how are PFK1 and fructose bisphosphatase 1 regulated by fructose 2,6-bisphosphate, and how are they affected, aka inhibited or activated? Explain how insulin and glucagon levels influence the levels of fructose 2,6-bisphosphate. So I'm gonna get this video up. Actually, no, this video is up already. Have you guys watched the regulation video I put up on YouTube? It's okay if you didn't, but I'm just saying, I went over this whole thing. That's why I'm gonna briefly touch on this, okay? So if you see on your little answer key that I made for you guys, I said, understand that PFK2, right? This is not gonna help you right now. Listen to me real quickly, okay? PFK2 is going to create fructose 2,6-bisphosphate. That is the enzyme that creates fructose 2,6-bisphosphate. And you know that if you have an increased level of fructose 2,6-bisphosphate, what gets activated? PFK1, right? So what she's trying to tell you is that fructose 2,6-bisphosphatase, not phosphatase, bisphosphate is a potent regulator of PFK1. It is made just to regulate the third enzyme in glycolysis. Let me ask you a question, because this is going to be mean to you, right? PFK1, what's the reactants to products for this enzyme in glycolysis? What does it do? What does it make? Right? Fructose 6-phosphate. Yeah, go tell me.
It's going to be fructose 6-phosphate, and it's going to turn into fructose 1,6-phosphate.
Yep, exactly. So look, first of all, I know you guys get a piece of paper on your exam, so that's probably why you weren't able to probably answer this question that I just asked you, and that's fine. I'm just saying in the future, you need to memorize all of this. Why not memorize it right now and get it over with? I'm literally, out of everybody who said they want to do pre-med, you need to know this off the bat. So when I ask you it, it's okay, I'm just your LA. You should know it already. So fructose 6-phosphate is going to go into fructose 1,6-bisphosphate. First of all, if it's called PFK1, that's phosphofructose kinase 1. Kinase is transferring a phosphate from ATP to get you another phosphate on the carbon 1. Do you see this, right? 6, 1, 6, right? That's easy. Not only that, but the kinase is coming from ATP, right? To make ADPPI. Does that make sense? So yeah, what's up?
Do you have a good way of memorizing which ones have magnesium?
So the thing is that magnesium cofactor is typically used, I guess, well, you're gonna see magnesium always be used when you have some sort of phosphate involved. I don't know the specifics of when it's used, but I do know that magnesium, because of the positive charge, is usually going to stabilize that phosphate because of the negative charge. So if I have ATP, right, 3 phosphates, 3 negative charges, right, I'm gonna have that magnesium there to stabilize it. Otherwise, you're gonna have a problem, too much repulsion, right? So I don't have an answer for you, but you should probably just know what it does. I've never seen a question where she's gonna ask you, where do you need magnesium? Well, magnesium is just a stabilizer, right? That's just my opinion. Yeah. Okay, so when we talk about PFK1, and we're trying to regulate this thing, we're talking about regulating it with fructose 2,6-bisphosphate. So what does that mean? I'm gonna write something on the board for you. Take a picture of it. It's even in your slide, or the thing the answer key. So, what I'm saying here is that PFK2, do you guys know what that is? What's PFK2? Just answer. Yeah. So, this is kind of a messy topic, I won't lie, okay? Fructose 2,6-bisphosphate is going to regulate PFK1. But you have to be able to make fructose 2,6-bisphosphate. Otherwise, how's it coming, right? You can't just bring it out of nowhere. No, you have to make it, okay? So to make it, we use PFK2. We use PFK2 to make fructose 2,6-bisphosphate. That's how you make it. So evidently, if I'm using PFK2, right, it's activated, then that will lead to an increase in fructose 2,6. I hate writing this stuff sometimes. it'll lead to an increase in concentration of fructose 2,6-bisphosphate, right? I mean, that's how you make it. Can I just show you something real quickly, okay? Fructose 6-phosphate uses PFK1 to put the phosphate on carbon 1. Just so you know, that's the same idea here, except it's fructose 6-phosphate uses PFK2 to put the phosphate on carbon 2. Okay, it's the same thing. You're just using a different enzyme. And this enzyme is going to create the regulator for PFK1. Do you see how I just tied that all together for you, right? I think that would be an exam question. I do think that would be an exam question. But my luck is that sometimes I say that and it might not show up. So I don't know. You got waxes on your last exam and that still has me shook. So, you see that, right? So if this is glycolysis, right? This is glycolysis, that's the mechanism for it. You know the opposite, right? Gluconeogenesis. Tell me what's the enzyme to go backwards from fructose 1,6-bisphosphate to fructose 6-phosphate. Yeah.
That's fructose 1,6-bisphosphatase.
Yes, it is. Right? So if we want to go backwards, I'm just gonna show it like that, right? We use FB PACE 1. Right? That's the enzyme you use for it. In order to take the phosphate off though, we're gonna add water, and then the phosphate will come off, and you get fructose 6-phosphate, right? It's called FB-PACE 1. That's how you do gluconeogenesis. Okay, now I'm gonna connect it again for you. How do you think you go from fructose 2,6-bisphosphate back to fructose 6-phosphate? How do you think you do that? What do you think is the enzyme?
FB2.
Yes, exactly. It's FB-PACE 2. Do you see that there's really no difference here? There's no difference in the enzymes you're using except for the day number. It's just the number that's different, okay? Now, let me ask you another question, okay? If I decide to activate FB-PACE 2, what do you think is going to happen to my levels of fructose 2,6-bisphosphate?
It's gonna decrease.
It's going to decrease. Yes, it is going to decrease. Right? Fructose 2,6-BP. Sorry, this is just our little mechanism. Just circle it. Okay. If fructose 2,6-bisphosphate levels decrease, and I just told you that if you increase your fructose 2,6-bisphosphate levels, then you activate PFK1. So what happens then if I decide to drop my levels of fructose 2,6-bisphosphate?
Sorry, keep going.
No, tell me. You had your answer ready?
PFK is inhibited. So
Yes, PFK1 is inhibited. So I'll tell you that we inhibit PFK1. Now, I'm not going to write this on the board. Tell me if I'm getting messy for you, okay? Because I'm just asking you questions. I need you to be interactive with me, okay? If I decide to inhibit PFK1, what do you think happens to glycolysis? It stops, right? I'm going to ask you another question now. If glycolysis stops, what do you think could be happening instead? What process do you think could be happening?
gluconeogenesis.
Gluconeogenesis, right? So what she's trying to say here is that, before I tell you what she's trying to say, let me erase this because this is giving me anxiety, okay?
Quick question.
Yeah, tell me.
How you said F26-bisphosphate regulates and makes PFK1,
No,
right?
I didn't say it makes it. I said it regulates it. So I'm saying that if I have an increased concentration of this, okay, if I have an increased concentration of fructose 2,6-bisphosphate, then evidently it's going to increase this. And when I say increase, I'm saying it's going to activate PFK1. Sorry, that's a bad word to use. It's going to activate it. It's not increasing it, it's activating PFK1.
Why?
Why? Why is it activating it? I have no idea. I just know it's a regulator for it. I'm just saying that there are going to be lots of compounds that are going to regulate things. I don't know, maybe like phospho-1 or something like that. It's just random products, okay? Random substances that somehow affect these enzymes in our metabolic pathways. So fructose 2,6-bisphosphate is literally just made to regulate PFK1. That's it. It's just made to regulate it. If I increase the concentration of it, then that means PFK1 is activated to do glycolysis. If I decrease my concentrations of it, then that means PFK1 is not activated. Instead, we'll do gluconeogenesis, meaning that I've activated fructose bisphosphatase 1. All right? Did I go too fast for this or no? We're good. Yes.
So fructose bisphosphatase 2, that's only activating FBPase 1. It's not inhibiting PFK1, or is it doing both?
Say it again. If
So-
you have lower levels of it? Or-
So the enzyme, in
Okay.
order to go from, like,
Oh, you're talking about these enzymes, right?
yes, yes.
Okay. Yeah, so if you activate PFK2,
Right.
then you basically activated PFK1 because you're increasing the concentration of this.
Right, I'm following that one. I'm referring to the one that's going in the direction of gluconeogenesis.
I think
You're
she's
talking about this one. Phase 2?
the arrow down.
Yes.
This,
that-
right?
Yes.
Yeah, okay. So if you decide to activate FBPase 2, that's saying that you're lowering your fructose 2,6 bisphosphate levels. If that's happening, you're inhibiting PFK1. If you inhibit PFK1 and glycolysis isn't happening, a different activity is happening. It's gluconeogenesis. You've basically activated FBPase 1. That's what it's saying.
All right, thank
You
you.
got it? Yeah.
Yeah.
So-
Okay, awesome. We good?
Yeah.
Okay, I'm gonna erase it real quickly. When you guys were going through the PowerPoint over this, was it confusing or no? Yes, no? Come on, let's talk. Yes, no? Yeah?
Yeah.
Okay. 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 So, what's the next question? Sorry, my thing's off. You guys are so mute. Like, why do you guys not talk? Okay. The next question asks, so I basically just told you how PFK1, right, and FBPase were regulated by fructose 2,6 bisphosphate, right? If you increase the concentration of fructose 2,6 bisphosphate, you're gonna activate PFK1. If you reduce it, you're activating FBPase 1. That's all it's saying, right? Activate one, stop the other. Activate the other, stop the other. Okay, that's it. The next thing they ask is, how is it inhibited or activated? I told you that, right? With the enzymes PFK2 and FBPase 2, right? I told you that as well. It's just I didn't make it so succinct, okay? The next question is asking, explain how insulin and glucagon influence the levels of fructose 2,6 bisphosphate. This is interesting. When she asks this question, she's referring to those enzymes I just said, PFK2 and fructose 2,6, or yeah, bisphosphatase. And that's where I'm going to show you this thing right here, okay? Okay, so I don't want to write this all down. PFK2, okay, and fructose 2,6 bisphosphatase, aka FBPase 2, okay? These two enzymes are on a polypeptide chain, meaning that as soon as I phosphorylate it, one of the enzymes becomes activated. As soon as I use a phosphatase, meaning I dephosphorylate it, another enzyme is activated. So, I'm gonna explain this really quickly to you, okay? Let's start with this side real quickly. What does glucagon mean in terms of blood glucose levels? Yeah, when you have glucagon, automatically please understand, you are having low blood glucose levels, right? That's what it means. So, just generally speaking, if you have low blood glucose levels, what do you think your body's gonna try to do? What metabolic process? Gluconeogenesis, right? Because you have no glucose, okay? So, we see here PFK2. What does PFK2 mean? What does this make? What does PFK2 make? Yeah, right? So if I have fructose 6-phosphate and I use PFK2, it's just gonna make fructose 2,6 bisphosphate, right? I go the opposite direction, right? What's enzyme?
PFKs.
FBPase 2, right? And it's gonna give me fructose 6-phosphate. Okay, so now you know what PFK2 does, right? Sorry. So if I have low blood glucose levels, it is telling me here that we're gonna use a kinase. It says we're gonna use a kinase, meaning that ATP, we're gonna take one of the phosphates and we're gonna put it onto the enzyme. Initially, it's just an it's just an alcohol hanging out, right? It's just an alcohol. Remember, I know you guys have a final, that's why I'm gonna say this. Do you remember your amino acids? Tyrosine, come on, the rest of them? Serine, threonine, right? Those are the three, okay? Those are the three amino acids that have those OH groups on them. You can phosphorylate those amino acids, okay? What I'm trying to say is that there's an alcohol group there, meaning that that's where you're phosphorylating. I just wanted to tie that back for you in case, I don't know if you forgot it for your exam, okay? Amino acids. So, OH is gonna get phosphorylated by ATP kinase, right? And what's gonna happen here is, right, the phosphate comes on. As soon as this phosphate comes on, we see that FB-PACE 2 is activated. What does that mean? What does it mean when FB-PACE 2 is activated? Tell me. Gluconeogenesis, but tell me in simpler terms, what does it do?
So it's gonna make fructose 6-phosphate.
Yeah, it is gonna make fructose 6-phosphate, right? That's what it does. And I said that if you increase your FB-PACE 2 levels, that evidently means that that's not active. PFK2 is not active, right? And we said that PFK2, ready? Let's do it again. If I have PFK2, what is it gonna make? Right there. I'm just asking you this so you talk to me. Yes, it's gonna increase your fructose 2,6 BP. What did I tell you if you increase your levels of that?
Regulates PFK1.
Right? And then we do glycolysis, right?
Yeah.
So, if I'm telling you that you phosphorylate this thing and this is inactive and this becomes active, then obviously you're not doing glycolysis. It's telling you go ahead and do gluconeogenesis, right? I told you that if glucagon is high, it means low blood glucose levels. It is saying that you want to phosphorylate this whole thing to activate this enzyme. When you activate fructose bisphosphatase, 2,6-bisphosphatase, okay, what's going to happen here is that you're going to go in the opposite direction. You want gluconeogenesis to happen. You're not activating PFK2. Does this make sense? Does this image make sense? Okay, that's good enough for me. So, now, what happens when you want to activate it? Obviously, you use a phosphatase. What's a phosphatase? Adds water to take off a phosphate. That's it, right? Phosphatase. So what's going to happen here is that in the case of insulin, what does insulin mean? High glucose levels, right? So when you have high glucose levels, right, we can use it for what? Glycolysis, right? All this glucose is, kind of catching up with us, right? So why not go make ATP with it? Why not make energy with it? You can do it. So what we're going to do here is that we're going to take the phosphate off of it. As soon as you take the phosphate off of it, what do you think is going to become activated? Yeah, I mean, it's written right there, just say it. Okay? It's going to activate PFK2. So it's saying that when you dephosphorylate this enzyme, this polypeptide chain, with both of these enzymes on it, when you dephosphorylate it, you're activating PFK2. When you activate PFK2, we are saying that we're going to do glycolysis because you've increased these levels. Does that make sense? Right? So you understand now how to regulate PFK1 with fructose 2,6-bisphosphate, right? You get it now? Yeah? Okay, cool. Yeah, tell me.
Could you, so you know how you went through each step of increasing and activating for PFK2?
Yes.
Could you do it for the opposite, right underneath it?
Want me to do it for underneath it?
Yes,
Okay.
please.
So if I decide to activate FBP PACE 2, right? It's telling you that essentially you have low glucagon, or high glucagon, meaning low VGL, right? That's what it's saying right there. What's going to happen here is that you're going to drop your fructose 2,6-bisphosphate levels. What happens when you drop your fructose 2,6-bisphosphate levels? Yep. You inactivate PFK1. But then what do you activate? What do you activate when you have low fructose 2,6-bisphosphate levels? Yeah, you're going to activate FB-PACE1. If you activate FB-PACE1, what do you think you're going to make? Or what process do you do?
Gluconeogenesis.
Yeah. Does this make sense now? So this is all of regulation. You want to take a picture, take a picture. But this is how you do it. Okay? If you write down these key stuff for your exam, I really think it's going to make it easier to answer questions. Yeah. I have this feeling like, I don't know why, I have this feeling that for this exam, she's going to pull out things that like maybe you didn't like think about. So, you guys remember sequestration of like hexokinase? I don't know why. I just feel like that's on the exam because it was rough for me when I was taking it. I don't know, like curveballs or something like that. Okay, so we're solid on this. Let's do the next question real quickly. Okay, so next question is saying, sorry, my thing is lagging.
Did you say sequestration of what?
Sequestration of hexokinase 4, I think. Yeah, something like that. It's in regulation too. Wait, you guys understand glycogen synthesis and, breakdown? That's really easy. That's probably one of the easier topics, in my opinion, for this exam. You guys know it, right? Oh God, okay. Another day. Anyways, so the next question is, the intermediates/reactions in the pyruvate dehydrogenase complex are shown. So I'm not gonna write that. You guys probably have it with you, right? In the study guide. In chemical terms, nucleophile, electrophile, oxidation, reduction, explain what is happening at each of the 5 steps labeled from A to E. So go to slide 13 in chapter 16. That's where so for my exam, what I did was I went to chapter 16, slide 13, okay? I memorized everything on that, on the PDC. Remember how to write it each time. Every time you write it, the mechanism makes more and more sense, okay? And that's exactly where she's pulling this question from. Yes, you have notes, but it's good to understand it still. So, the first part is A, right? Can somebody explain to me what A is? Okay, so for A, right? I mean, the answer's right there, but it doesn't matter. So A, the better answer would be that you kind of want to describe it in terms of nucleophile and electrophile. In my opinion, the only places that you're going to probably talk about oxidation reduction would be in those redox steps of probably D and E. D and E, because you have those cofactors of NADH and FADH2, those are places where if she asks you, hey, talk about redox, talk about oxidation reduction, you're going to probably look at these types of cofactors, right? Because you can see easily that where the oxidation is happening, where the reduction is happening. In the cases of A, B, and C, we want to talk about it in terms of electrophile, nucleophile, and honestly, if you want, put in a little bit of extra stuff, just make sure it's right. Like transistor, yeah, what's up?
Yeah, so do you want somebody answering now or after?
Give me 1 second, I want to say something. You guys know what transesterification is? Okay, then we'll not say that, okay. Okay, yeah, if you want to explain A to me.
Yeah, so because we have the C double bond, the ketone, that's a good electrophile for the substrate right there.
Yeah, the carbon, right?
Right.
When you have that negative, it's a nucleophile, comes in and attacks it, tetrahedral intermediate, whatever, maybe it'll drop, then maybe you get the double bond again, right? So what she's saying here in step A, okay, is the TPP cofactor. What's TPP, guys? It transfers 2 carbon units, okay, into E1. That's what TPP does, okay? Pyruvate dehydrogenase complex is E1, E2, E3. E1 is going to have TPP. That's A, okay? E2 is step B. That's when we talk about lipoic acid, aka lipoiolysine, right? See the lysine? It's actually attached there, but she didn't write it. And then we talk about step C, CoA, right? That's also an E2. I've said 3 coenzymes so far. Then obviously, sorry, I said E2. Then E3 is where you have FADH2 and NAD+. That's the last 2. So do you see it? Yes? No? Maybe so? Okay, I'll take it as yes. Okay, so yeah, that was right? So the carbon on the TPP is nucleophilic, attacks the electrophile carbonyl on pyruvate, transfers 2 carbons, okay, and attaches it into E1 so you can do pyruvate dehydrogenase complex. You cannot use any enzyme if it is not attached, right? Meaning that if I don't have pyruvate attached, if I don't have that reactants attached to the enzyme, how do you think the enzyme is going to work? It won't. It has to get attached first, and that's what TPP is doing. It's transferring 2 carbon units in, and you see the 2 carbon? It's right here. Carbon 1, carbon 1, carbon 2, right? It attaches 2 carbons, and then we see CO2 leave, but she didn't write that, so, but it's there. CO2 leaves when you use TPP, all right? Can you tell me about B? Anyone? what's happening with B? Let me tell you, okay? So, this is called lipolysine, okay? Lipolysine is the first coenzyme of E2. The whole objective of this coenzyme, okay, is to kind of get it ready to get the CoA attached to it. That's what lipolysine does. It's just trying to get it ready, okay? So what's happening here is that, do you notice that you have this disulfide bond right here? That means it's fully oxidized. Lipolysine has 3 conformations. I can have it fully oxidized. I can have it half oxidized, or half reduced, whatever you want to call it. And then I have a fully reduced. There are 3 versions of this molecule, and that's when it goes through PDC, okay? So, at first, it's fully oxidized, right? Now, all of a sudden, as soon as I attach, okay, this kind of thing right here, okay? Oh, it's really ugly. But it's like you're attaching these next 2 carbons onto the lipolysine. That's what's happening, okay? So a good way to say it is that, well, honestly, even I didn't describe it in terms of nucleophile and electrophile, but looking at it right now, it's probably going to be the sulfur attacking right around, let me even find it, right here. Yeah, it's probably gonna attack right here. The same carbonyl, C double bond, okay? It's still gonna attack there. So this nucleophile, right? Because sulfurs are nucleophilic compared to carbons. It's gonna attack here, and then you're gonna get the half-reduced version of it. Meaning that as soon as you add the 2-acetyl, or the acetyl group, right? The 2 carbons, as soon as you attach it onto the lipolysine, it breaks the disulfide bridge. As soon as it breaks the disulfide bridge, and you attached the 2 carbons onto it, you're gonna get the half-reduced version of it. Do you see it? Or half-oxidized. It goes both ways. Do you see it? Yeah? Yes? No? Just say yes. Yes, I see it. Okay, yeah. Okay. So finally, when you get the half-reduced, half-oxidized version of it, you're gonna add CoA. CoA is still in E2. What do you think is gonna happen? It's just gonna attack it. It's gonna release this lipolysine group, and you get acetyl-CoA made from E2. Write that down. Acetyl-CoA comes from E2. It doesn't come from E3, it comes from E2. Okay, that's where you get that product. But now the problem is that how can you get lipolysine, okay? Because now it's fully reduced, right? Because you took off the acetyl-CoA essentially, right? You took it off, you made it. Now you're in the fully reduced version of it. When something is fully reduced, it has hydrogens, it has those electrons, right? What do you think you can do with it? We can put it onto FADH, right? FADH is a prosthetic group. What does a prosthetic group mean? It stays, it doesn't leave. FADH doesn't leave. When it gets those 2 electrons right here, HH, right? And it gives it to basically FAD, you get FADH2. Notice FADH2 never leaves. That's because it's a prosthetic group. Prosthetic groups are fully, they just stay, they don't go away. That's why we have to bring NAD plus and transfer those 2 hydrogens, those 2 electrons, right? Onto it so that it can go where? Where do you think
Electron
NAD
transport
goes?
chain.
Yeah, electron transport chain. Okay. Does that make sense? I just kind of described it, but I guess maybe. Honestly, the answer key is there. Is there anything in the answer key that you're not understanding? I just felt like maybe if I explained it, it would make more sense. Really, this is the place where redox happens. She'd want you to talk about oxidation reduction in step D and step E, right? Once you get these 2 hydrogens off of it, you go back to the lipolysine. It gets fully oxidized again. That's how you continuously regenerate this process. It goes from fully oxidized with the disulfide bridge. We go half oxidized. We release the acetyl-CoA, and we get fully reduced now. Take these hydrogens, give them off to E3, electron transport chain after, and then you remake it again. Make sense? Yeah? Okay, cool. So, a liver cell is carrying out glycolysis under aerobic conditions. A very specific and potent inhibitor of ATP synthase is added and completely inhibits this enzyme. So, can I just say something real quickly? Remember inhibitors, competitive, uncompetitive, all those stuff? I really have a feeling she's gonna mix something like that. Do you see what happened here? I really think she's gonna mix questions. So like, if I have 10 questions, maybe part A will be something like, oh yeah, I have a competitive inhibitor that's gonna, I don't know, work with the ATP synthase. What's gonna happen? Blah blah blah. Can this thing still happen? Right? If you have a competitive, that's just a hypothetical like question, whatever. But I'm just saying she's gonna mix units because that's a mixing of units right here. Okay? The idea of having an inhibitor. All right. So indicate whether each of the following statements about the effect of this inhibitor is true or false, and explain why. So the first one, right? A. ATP production in the cell will drop to 0. Before I even ask you the answers to this question, what is the question even saying? Like, can you tell me information about it? What is it saying? Yeah, tell me.
So it's like asking about complete production of ATP, not specifically ATP synthase.
Kind of.
Okay.
Sort of. Not really, but close. It's close. It is specifically talking about ATP synthase.
Oh,
If she was talking about electron transport chain and ATP synthase, some of the answers would actually change for this question. So she's just looking at ATP synthase, okay? So you've done electron transport chain, we're at ATP synthase. What does ATP synthase do? Mix ATP, okay, yeah. I just wanted to see. Okay, so when she says that you're adding, first of all, a liver is carrying out glycolysis under aerobic conditions. So she's saying that there is oxygen right now, okay? If there's oxygen, what happens? You're gonna go from glycolysis to citric acid cycle to electron transport chain. If she said anaerobic and she asked this question, honestly, some of these answers would not even you would probably be saying false to them. So watch out for your answers, okay? If she said it was anaerobic, you probably are gonna say false for most of them, but it's still aerobic, okay? So just clear that up, okay? So the first question says, is ATP production in the cell will drop to 0? Will it drop to 0 if ATP synthase is inhibited?
Yes.
Yeah, it will, right? I mean, it's just saying right there that if you have an inhibitor of ATP synthase, it's not going to work. If it's not going to work, do you think ATP is going to be made? No, it's not. Yeah.
But isn't like some ATP made from like actual glycolysis?
Yeah, sure, but she's talking only about ATP synthase. That's just the enzyme. Yeah. So you got the first question. Second question. A rate of glucose consumption by this cell will increase sharply. Yes or no? Will it? If you say true, raise your hand. Just want to see. True, it will? Okay. False, if it won't? Okay. So, the rate of glucose consumption by this cell will sharply increase. True. That is true. And I'm going to explain why. So let's think about it like this, okay? If ATP is not being made, right? ATP is not being made because we have an inhibitor on ATP synthase. The body is going to think, oh God, I don't have enough energy in my body. The only way I can start getting energy is to break down glycogen, right? My glycogen storages, get the glucose, and start burning it off in glycolysis. The body's going to think, okay, I need to take as much glucose as I can to start making energy because there is no ATP synthase. There's an inhibitor. It's not working, okay? That's why we sharply increase our consumption of glucose because the body is confused, okay? I'll give you an example. If glucose, right? Glucose makes ATP, right? It does. I mean, evidently, it goes down and makes lots of ATP, right? If the body thinks that there's no ATP done, right? There's no energy is being made. Glucose is going to continue going through that direction because think about free energy, guys. If your products are decreasing, your reactants are going to accumulate, meaning that they're going to continuously keep pushing to products. But if the products are never being made, right? ATP is never being made, then glucose will continuously be consumed because the body doesn't realize it. Does that make sense? Let me show you, right? So glucose, right? Goes citric acid cycle. Ooh, let's go. Electron transport chain. ATP, right? That's what happens. All of a sudden, if I take this out, the body's gonna think, oh God, I gotta keep increasing this. I gotta keep going through this process. But it's always gonna stop right here. It's gonna stop at ATP synthase. Ooh, ATP synthase. It's gonna stop, right? So you're gonna keep increasing it. you see what's happening? Makes sense, right?
Mhm.
Okay. Now the next question is asking the rate of oxygen consumption will increase. Will it? Will the rate of oxygen consumption increase if you're not making a lot of ATP? Yeah, false. It's not going to increase, right? Think about it, like, to do the electron transport chain, it requires oxygen, right? To do it. I mean, to go from citric acid cycle all the way to ATP requires oxygen. As soon as I'm telling you that ATP synthase is inhibited and you're not doing it, right? Oxygen will not be used, right? Because the enzyme itself is not working, it's not doing anything. So oxygen isn't going to be consumed to even make ATP. You need oxygen to make ATP in the electron transport chain. As soon as I take off the enzyme in electron transport chain, oxygen's not being used anymore. It's not. Am I making sense? Because I'm talking more than I'm writing, honestly, today. But if it's not making sense, I have no problem going through it again. All right? Yes, Sam?
Can you just repeat the oxygen?
Yeah, it's okay. So we're saying here that if glucose is going down to ATP, right, to the very end, we're going from citric acid cycle, electron transport chain, to ATP evidently, right? It's going to use oxygen. It's an aerobic process, right? As soon as I stop using the enzyme in ATP synthase, I stop using that enzyme, right? I inhibit that enzyme, it's not working anymore. Then that means that there is no oxygen even being used in this process, right? Your oxygen consumption is not increasing, because if you're saying it's increasing, then you're saying ATP is being made. That's not happening. You're not making ATP, therefore oxygen is not being consumed. Does that make sense now? Yeah? Okay, cool. The last question, or not the last question. The citric acid cycle will speed up to compensate. True? Right? True or false?
True.
You say true, right? Anyone explain why? And it says it speeds it up. That's what it said. And it was a pretty, it was, NCBI, NIH, that's what it said. You would be using the citric acid cycle more often, right? If you're not making ATP, right? Because low ATP levels mean that I want to do the citric acid cycle to make more ATP, right? So then the last one says is the cell will switch to fatty acid oxidation as an alternative to glucose oxidation, and the inhibitor will therefore have no effect on ATP production. True or false? Why?
Because the only type of ATP we can use is from sugars, not fats, and so it's only going to make what's being used in the glycerol.
Interesting answer. False, but that wasn't the answer I said. But no, I agree with you. That makes sense actually. But think about it like this: when you do beta oxidation, you get that acetyl-CoA, right? Acetyl-CoA is always going to go into the citric acid cycle, right? As soon as you go into the citric acid cycle, the next step is electron transport chain. So no matter where, even if you did beta oxidation, even if you're trying to break down those fatty acids, right, to make acetyl-CoA, acetyl-CoA is always going to go through the citric acid cycle, okay? As soon as it goes through the citric acid cycle, it hits electron transport chain. It hits that ATP synthase inhibitor. So what's going to happen? You're not going to make ATP still, right? Does that make sense?
Mhm.
Okay, cool. Wait, can you say your answer one more time? I just wanted to hear it.
Yeah, so I when I answered, I
Uh-huh.
just didn't do fatty acid necessarily, but I did triglycerol.
If it's
So
a
I had
triglycerol,
then that's fine.
well, even if you did triglycerol, see, the thing to this question is she says fatty acid oxidation. When we say fatty, we're thinking about beta oxidation, yeah. But if she said maybe if the cell were to switch to triacylglycerol and we were breaking that down, catabolism of that, and let's say she says let's not talk about the fatty acids, then yeah, that would be okay. Answer. Okay, are we good? Yeah. Okay, cool. The next question: how does? Actually, let's even move this to the. Okay, the question is, how does the proton motive force created by electron transport change, ooh, she did not say that right, electron transport chain, lead to the generation of ATP in as much detail as possible, describe the enzyme responsible and how it couples to the PMF with ATP synthase. She's just saying be detailed about it, like a lot of times. So can somebody explain to me then what the proton motive force does? What is it?
The proton motive force is basically taking the hydrogens from the inner Higgs matrix and pushing it out, and that's going to create a force where you can lead, where it's going to have a high concentration outside of the cell to a low concentration. So as you go through that, it'll allow enough energy to make the ATP necessary.
Yes, that is perfect. Yeah, that's exactly what it does. Does everyone understand what she just said? If you didn't, it's okay. Just say, hey, I don't understand it. Can you just do it one more time? Otherwise, I'm gonna keep going. So tell me.
Can you do it?
I'll do it one more time. Okay. So what she's saying here is that electron transport chain, guys, right? We have that first part, oxidative phosphorylation. The oxidative portion is when we're talking about electron transport chain, right? We're talking about all those NADH cofactors. We're talking about those FADH2, right? It's going through complex 1, complex 2, complex 3, complex 4, right? It's going through those complexes, and then obviously we're going to go to the last electron acceptor, oxygen, reduced to water, right? But throughout that whole process, what's happening here is that you're getting, I'm going to draw it real quickly for you. What's happening here is that you're getting all these complex 1, complex 2, complex 3, complex 4. You're getting 4 hydrogens pumped through. Wow, that was bad H. 4 hydrogens pumped through complex 1. Nothing pumps through here, right? We have 4 hydrogens going through complex 3. And then obviously 4 coming through here. Actually, I want to make sure I'm right on something. 1, 2, 4. Technically it's 8, actually, because you do the Q cycle twice. Okay. So you're pushing all these hydrogens across, right, the inner membrane, okay? This side right here is called the N side. Why do you call it the N side?
Negative.
Yeah, why do you call it the P side? Positive, because you're getting lots of hydrogens on the other side. So what's happening here is that as you're going through this process, right, all these electron carriers are getting given off to other carriers, right? You're going from NADH to going to ubiquinone to make ubiquinol, right? Coenzyme Q, that's an electron carrier. You have cytochrome C oxidase going to cytochrome C reductase. These are just all electron carriers. At the end, you take all those electrons, put it on complex 4, right? And you make water, right? So when you're doing this, it's a favorable process. You're going from these high electron affinity carriers, okay? Going from low to high. That's why they continuously keep moving. You release the energy. That energy that gets released is gonna move hydrogens across to the P side. Once you get all those hydrogens accumulating on that P side, you obviously have this next side right here, right? The ATP synthase. Oh man, I hope I read this right. So, whatever, this is my drawing. This is called the F1 subunit. This is called the FO subunit. So now, after we've done the oxidative part, right, we're gonna do phosphorylation. Phosphorylation is where you make the ATP. When you make ATP, it is actually a very unfavorable process, meaning that ADP to PI, or ADP plus PI makes ATP. It's not that good. You need energy to do it. Because remember, hydrolysis of ATP, when you break it down, is a very favorable reaction. It's like negative 34 kilojoules or something like that per mole. Okay, it's very, very favorable. So what we're trying to do is make ATP favorable. You make ATP, by the way, in F1. That's where you make it, okay? It makes ATP right here. And the way you make it is, you get all of these hydrogens on this side. Oh wow, I'm so sorry, that did not look pretty. I'm just using positives as hydrogens, right? You get all of these hydrogens on the outside. They're gonna go from a high concentration to a low concentration gradient. They're gonna go through this F0 subunit. As soon as it goes through the F0 subunit, you have this gamma stalk right here. The gamma stalk, if I'm looking at it bird's eye view down, is gonna turn like this. It's gonna turn. That's where we talk about ATP being made. It's called the binding change model. Do you guys know what the binding change model is? Really? Explain it to me. Yeah.
It's like the configuration of alpha and beta rotates so that it generates ATP or ADP, whatever.
How many ATPs would you make then when you go through one full cycle? 3. How many hydrogens would you be making or pushing through from
9.
this side to this side?
9.
9. Yes, you use 9. Okay. I'm still gonna go over it. Good job, though. That was good. So yeah, as soon as you have these hydrogens coming through, right? For every 9 hydrogens that go through FO to F1, the gamma stalk is gonna rotate. Okay? It's gonna rotate so that your beta subunits, okay? Beta subunits are where ATP is made, it's released, and then you have the reactants, right? ADP plus PI. I'm just talking, I'm gonna show you an image soon. Once this thing spins, right? It's gonna make 3 ATP when you add 9 hydrogens going through, right? Because remember, P side to N side. So now let me show you the image that will help you. This. I think Sohail, you asked one time in class, why is it 3 ATP? I'm gonna explain to you. So what you have to realize is that this is the binding change model, okay? For 1/3 of a rotation, you make ATP. 1 ATP, you use 3 hydrogens pumped from the P side to the N side. So you see, it goes from, well, we're going this way, okay? P side to the N side. So, notice that all of the ATP, right? The ATP is usually being made, it's usually having the reactants, right? Which is ADP plus PI, okay? And it's usually being released in the beta subunit, not the alpha subunit, it's the beta subunit. It's right here, beta, beta, beta. For every beta subunit, you have a what? An alpha subunit, right? It's just there. I don't really know what maybe it has to do with stability. I have no idea. But, if we're starting, let's start with this one right here, okay? We're gonna have 3 hydrogens come from the P side to the N side. 3 hydrogens go in, it moves it once. This is the rotation we're in, right? 3 hydrogens from the P side come to the N side, we rotate it. When we rotate it, 1 ATP in the first subunit is released, okay? In the second unit, you are having the reactants. You just have the reactants made, right? And then, in the third beta subunit, you have ATP ready. It hasn't been released yet though, okay? That's just when 3 hydrogens come in, it gets in this rotation, it gets in this conformation. As soon as I add another 3 hydrogens in, it's gonna move again. Every time it moves, it's going to release the ATP that's right here. You see it? It gets released on the top, right? It's made, I'm gonna release it, and then I see that this unit that was empty here is now gonna get the reactants in it, ADP plus PI. It's gonna get the reactants in it because I shifted it, okay? And then the next subunit right up there, remember when you had the reactants here? It's gonna make ATP once another 3 hydrogens come in. Does that make sense so far, what I'm trying to say? If I do it again, I shifted one more time. This is the last one, the third rotation. I add another 3 hydrogens from the P side to the N side, right? From the intermembrane space into the matrix. What's happening here is that I'm gonna take the ADP-PI right there on the left. I'm gonna make ATP with it. I make ATP with it. Do you see the ATP that was ready next to it on the right? That's gonna get released. You already made it. Release it, okay? Then, the ATP that was released is gonna get the reactants back again. So do you see how you just made 3 ATP, right? In one rotation? And in one rotation, I used 9 hydrogens to pump each time to move it, right? So it makes sense now, right? Binding change model, easy. Okay, cool. Let's see the next question. Do I have any questions on that? No, right? Easy?
The whole thing is one rotation, right?
This whole thing is one rotation. She's talking about a third of a rotation? Yeah, it would be just 3 hydrogens. Yeah.
Thank you.
If you want to take it off, please. Yeah, just take it.
Thank you.
Yes, yeah, what's up?
For like the hydrogen amounts, is that for like 1 NADH? Like on the whiteboard, the complex?
I'm sorry, this?
Yeah. Like
So-
if 1 NADH goes in,
Yeah, it's
and
1
then that's like
NADH.
for the whole thing.
Yeah, so it's 1 NADH, yeah, so if I have 1 NADH, it's gonna go to NAD plus. The hydrogens are gonna go through those sulfur iron clusters, and then it's gonna go to ubiquinone, QH2, that's the electron carrier, and then as that happens, yeah, you push 4 hydrogens through.
So then for complex 3, you put in that like QH2 that we just made, and
Yeah,
then
I
another
mean,
one.
in complex 3, the QH2 can be coming from complex 1 or complex 2, yeah. And then you use that to do the cytochromal oxidase to reductase and break it to 4, right? Okay, cool. I'm not gonna go over the Q cycle today because I think I went over it a lot once in class and in the, review section. I'll post the video up, it's coming soon. I'm just really busy and stuff. Okay, write a balanced equation for the degradation of a 20 carbon saturated fatty acid into acetyl-CoA. Include all necessary cofactors in the equation. So what I did here I wanted to, so in orange, I think you guys can see it, yeah. In orange, what I did I just I wrote the general mechanism, okay? So what I'm saying here is that when you're degrading a 20 carbon saturated fatty acid into acetyl-CoA, you obviously are gonna have to do beta oxidation. But notice that she said acid, fatty acid. She did not say fatty acyl-CoA. If she said fatty acyl-CoA, I would skip all the steps from here to here. I'd skip those because you already have fatty acyl-CoA made, right? And you would start with beta oxidation. Watch out for words. Acyl-CoA versus acid are very different, and you're gonna get a different amount of ATP made for it, okay? So, let's see. You guys understand how to do it? You know how to do beta oxidation for this one? Okay, I'm gonna do it right now, okay? I think I had one student, actually, you know what? I'm not gonna expose them today. Okay, so let's do it real quickly. So, first of all, if you have a fatty acid, it cannot go through the matrix. It cannot go through the matrix. You have to convert it into a fatty acyl-CoA group. I have to take off that acid, the O-, and I'm gonna put CoA on it. How do you do that? You use, maybe I should write it out for you. If I have a fatty acid, I'm gonna denote it as Fa, okay? And I wanna make fatty acyl-CoA. It's the same idea. All I'm doing here is that I'm changing this O-, and I'm making, that's it. And obviously you have your R group too, right? Because it's super long. And what do you think the enzyme is for this? Lipase. Not lipase. Fatty acyl-CoA synthase. Yeah. Huh? Yes, you said it? You said fatty acyl-CoA synthetase, right? Oh, that's okay. That's okay. You're gonna use fatty acyl-CoA synthetase. I remember saying this. I say this every single time because if all of you pre-med students, you need to know what synthetase means, okay? Synthetase means that you're using ATP to make this reaction happen, meaning that I'm going to use ATP for this reaction right here. And that's how you're going to put the CoA on it, okay? A synthetase puts it on. A synthase just combines, doesn't use ATP. Synthetase does. I say this every single time so I can ingrain it in your head, okay? So now you made the fatty acyl-CoA group, that's great. But the problem is that what happens when there's too many carbons on your fatty acyl-CoA? Do you think it's gonna go easily into the mitochondrial matrix to do beta oxidation? No, it's not. If this chain is bigger than 12 carbons, okay, if it's bigger than 12 carbons, we need to use this thing called the carnitine shuttle. Can somebody explain to me what the carnitine shuttle is?
I can try.
Yep, tell me.
You basically need to get it into the matrix, and so you swap out I think it's the CoA for the carnitine, you pull it through, and then it comes off at some point, and then you'll eventually get it back to the starting point.
Yeah, that's literally it. Like, all it's saying is that, literally, I draw this picture, I think I drew it last time too. Okay? The thing is that anytime you want to do beta oxidation, it's not that it has to go through the carnitine shuttle. That's not what it's saying. When you do beta oxidation, you need to have it into a fatty acyl-CoA group. It doesn't matter how long it is. It doesn't matter how short it is. It needs to be a fatty acyl-CoA. It has to have that. If it doesn't have that, you don't do beta oxidation. But now, once you have this fatty acyl-CoA, it's ready for beta oxidation. The problem is how do you get it into the matrix, right? So, if it's a very long chain, more than 12 carbons, I need to use the carnitine shuttle. If it's less than 12, then it's just going to easily diffuse, and you're going to be able to do beta oxidation. In this case, you can't, right? Because there's 20 carbons. So what's going to happen is that this thing, I drew it last time and it was so bad, okay? But basically, I have this carnitine right here, right? The carnitine, and this is my CoA group, right? R group. What's going to happen here is that the CoA is going to come off, and the carnitine is going to come on, right? And it's going to drop this fatty acyl-CoA. It's going to drop the CoA group and it's going to add a carnitine. When you add the carnitine, it's going to go through the matrix. And evidently, you're going to get something like this, carnitine, right? And then the R group. But now, it gets through, right? Now we're going to go through the next transporter, and I get it right here. Carnitine is on it still, right? My R group. The problem is that I told you that you have to have fatty acyl-CoA to do beta oxidation. So what it's saying here is that once you pass and you're inside the matrix, the carnitine is going to fall off, and you're going to add the CoA back onto it. So the CoA is going to come back onto it, and you're going to get what you originally started with. Does that make sense? Right? Easy. I really think it's that easy. All right, so now I explained this to you. Okay, you have your fatty acyl-CoA, it's ready for beta oxidation. I mean, now I'm going to have to show you how to cut this thing in. Okay, I'm going to show you how to cut it. Okay. By the way, have you guys done beta oxidation with three double bonds? She's only done 2 double bonds, so I'm just wondering if you've done 3.
I asked her and she said that won't be on.
Okay, good. I'm glad. Okay, I was gonna ask her too, because let's just real quickly do this thing, okay? So I have the CoA here, carbon 1, carbon 2, carbon 3, carbon 4, 5, 6, 7, 8, 9, 10, 11, 12, 14, 15, 16, 17, 18, 19, 20. Okay, beta oxidation, how many acetyl-CoA units does it cut?
2 carbons.
What's the objective of beta oxidation? You need to know why you do stuff. That way you can answer questions. Why do you do it? Why do you do beta oxidation?
To make acetyl-CoA.
Yeah, you want to make acetyl-CoA. The other thing is that sometimes the body has to find other ways to break down, right? To make energy. You know, people who are on that ketone diet and stuff, who take less glucose. By the way, that's a terrible diet. Never try that, okay? Especially if you're an athlete or something like that, do not do that. That's gonna kill your energy levels. It's awful. That's just my opinion. So basically you're not eating glucose, right? You're looking into these fatty acid, these triacylglycerols, right, inside the adipocytes. It's the fastest way, basically, to break down fat, right? Because it's breaking down fatty acids. Do you guys remember ketones? Have you guys studied ketones enough, at least? You know, acidosis and all that stuff. Can I just quickly talk about it? Can I quickly talk about it? It's actually very interesting in my opinion, okay? So let me talk about it, okay? So people who are on this diet, right? They eat high fats, butter, fried oils, oils, things like that, right? So what's happening here is that you're not taking glucose, so you're not gonna be doing glycolysis in your body. Yes, you're gonna have glycolysis, but not to the extent of beta oxidation. So there's a problem though. When you do glycolysis, by the way, this is in the slides, that's why I remember this. Glycolysis is the fastest way of getting energy. That's why people who are athletes, like you do lacrosse, they eat like pasta, or they eat some sort of fast energy yielding. The fastest way to yield energy is through those carbohydrates, right? That's what they do. No one eats a fatty meal before any race. That's just impossible, right? Because it's so slow to break down. When we talk about this ketone diet and all that, right? Keto diet, yeah. What's happening here is we're going into these fatty acids, right? We're going into the storage, adipocytes, triacylglycerols. We're breaking it down, okay? And we're getting these fatty acids. When you get those fatty acids, you're doing beta oxidation, right? The problem is that, okay, you're getting acetyl-CoA, whatever. There's gonna be a point in time, okay, where your body's gonna need more energy. It cannot just, it's so slow to the point where your body is probably gonna be doing and making ketone bodies. What do you think ketone bodies are? Basically, I'll just tell you what they are. Ketone bodies, okay, are just another method of producing energy. It's this thing called acetate, acetoacetate, and dihydroxypropanone. butyrate, yeah, butyrate, okay? You have these ketone bodies, okay? And what they're gonna do is that because you're not having a means of making energy as fast, it's gonna take those ketones and try to produce energy. The problem is that if you have too much ketones in your blood, you're gonna get ketoacidosis. You know what they talk about when you're, are any of you guys EMTs? It's okay. So, oh, you work with them?
Yeah.
Okay, I don't know, later, I'll ask you later. Anyways, what's happening is that when you get these ketones building up, a lot of EMTs to figure out what's happening to this person's body, especially people who are going through having low glucose levels as well, right? Hyper, I can't even remember that one, it's been a while. Anyways, the point is that their breath is gonna smell really, really fruity. It smells really, really fruity, and that's how they can pinpoint this person's in ketoacidosis. You gotta give them some glucose because they're having can somebody tell me, remember, what's the? Hypoglycemic, that's exactly the word. Hypoglycemic, meaning low blood glucose levels. Their breath smells fruity. That's how I know there's a lot of ketone bodies they're doing.
I thought it was their breath smells like acetone.
It's fruity actually. It's both. Because I mean, acetone and, I mean, it's acetoacetone, yeah, it's fruity too. It's mainly fruity, you can't really tell. Usually with acetone, it's with alcoholics, right? So they have that as well, but mainly it's fruity. Yeah. So yeah, that was cool, right? Okay, so let's break this thing up, okay? So what's gonna happen here is that you're gonna break it by 2 carbon units. This is the easiest way to do it. I don't know if she's done it either. Count 2 carbons, break it. 2 carbons, break. 2 carbons, break, 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 break. Every slash that you see is 1 round of beta oxidation. So 1, 2, 3, 4, 5, 6, 7, 8, 9, right? You have 9 rounds of beta oxidation. Now the next question would be, how much acetyl-CoA do you yield? Well, we get 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 acetyl-CoA is made, right? So, I tell you, 10 acetyl-CoA. Now you have to understand how much ATP is made in each, or not even ATP, how much, because you're writing the reaction, right? You have to figure out how much FADH2, NADH, ATP, all of that. What's the net reaction? That's what she's asking. You're lucky you don't have to, figure it out right now, okay? So 9 rounds of beta oxidation. In 1 round of beta oxidation, how much NADH and FADH do you make? 1 each, yeah, 1 each, guys, yeah. So we'll do 1 NADH, right? And 1 FADH, 2. I'm going to multiply this by 9, right? Because you have 9 rounds of beta oxidation. Does that make sense?
Mm-hmm.
When I do 10 acetyl-CoA, you got to put this into the citric acid cycle, right? I mean, that's how it works. I'm just doing extra right now. Citric acid cycle, 1 round. How much NADH and how much FADH and how much ATP is yielded? 1 round.
10 ATP.
What did I say? I said 10 ATP, right? Yeah. Oh, you said 10 ATP, right? Okay, but I'm asking about FADH2 and NADH. I'm asking 1 round, not 10 rounds. 1 round. How much NADH is made and how much FADH2 is made?
2. Is it 3 NADH,
Yeah.
1
Yeah.
FADH2, and then 1 GT.
GTP, ATP equivalent, same thing, yeah. So it'll be 3 NADH in 1 round, 1 FADH2, and we'll say 1 ATP for now. Same thing, it's equivalent. Multiply this by 10, right? And you get what, 30 NADH, 10 FADH2, and you get 10 ATP. This is not ATP, this is just how much of these you have. You haven't converted it yet. And here you have 9, 9, right? Okay, now let me read the question because I went overboard. Let's see. Write a balanced equation for the degradation of with all cofactors. Oh God, just kidding me? Okay, I forgot I did all of that. Okay, so the next thing is that because you have, okay, oh my God, this is so much work to do. I really apologize, I'm a little bit tired as well. I got finals and all this stuff. So what's happening here is that you have to obviously go to acetyl-CoA as well, right? In order to make acetyl-CoA, you also have to add 10-CoA during beta oxidation, right? Because in the fourth step of beta oxidation, you also have to add that CoA to break it in half. Do you know what I'm talking about right now? Say if you don't know, I'll say it again. Not really? Okay. In beta oxidation, you have step 1, step 2, step 3, and step 4. Step 1 is when you do the oxidation reaction, which technically is reduction to FADH2, but we're talking about metabolites, so that's what we're saying. We do we make FAD to FADH, right? In the first step of beta oxidation. In the second step, we what? Add water, right? Hydration reaction. In the third one, we do what? Yes, we make NADH, right? NAD plus makes NADH. Oops, plus H plus. The last step, you add what? CoA. And why do you think you add CoA? To break it up. Exactly, thiolase, right? Thiolase. This is just one round of beta oxidation. But we told you that you have how many rounds?
9.
9 rounds, right? You have 9 rounds, but the thing is that you generate 10 acetyl-CoA. If you generate 10 acetyl-CoA, how many CoAs do you think were added? It's 10, right? It's 10. If you make 10 acetyl-CoA, you need 10 CoA. Otherwise, how do you make 10 acetyl-CoA, right? Okay. So you gotta add, let's write this down here. Oh, this is messy. Okay. I'm gonna erase this, is that okay? Okay. So if I'm writing this net equation so far, I'm not gonna say the first part, I have 10 CoA groups, right? We know that, 10 CoA groups, for sure, right? Because you made 10 acetyl-CoA, you need to add that, for sure. We know that for a fact, okay? The next part is that you have 9 FAD. Where do you think that came from? Right here. Well, technically to make FADH2, you need 9 FAD, right? That's a fact. Like, I don't know if I should even explain that. I don't think I need to, okay? You're gonna add 9 FAD, right? To make 9 FADH2, right? Easy. Now, the thing here is that I also have 9 NAD+, right? Don't look at this right now. This is just extra, okay? We're just talking about the oxidation part. We're not talking about it going yet into the other part, into citric acid cycle. So then I'm going to use 9 NAD+, right? Because you had to make 9 NADH. Now you use 9 H2O. Where do you think the H2O came from? Which step in beta oxidation?
2.
Second step, yep, 9 of them. 9 H2O, right? Listen, I know a lot of people want to put 9 here. It's just impossible to put 9 here because you made 10 acetyl-CoA. If you made 10, you need 10 CoA, okay? The reason why these are all 9 is just because it has to do with the idea of the oxidation, right? It's just the rounds of oxidation when we're talking about FAD, NAD, and H2O. When we talk about genuinely the acetyl-CoA, I mean, it's right here. Like, you see, like, that, it's like literally 10 of them. And you need to add 10 CoAs to it. I think that's the best explanation I can do for it. Okay, so now, she does also include ATP. Where do you think this ATP comes from? Where do you think it comes from? It comes from, that's why I said it's good to write this thing down. It comes from when you made it into the fatty acetyl-CoA, because you started with the fatty acid, right? You started with that fatty acid. When you break down the fatty acid and you put the CoA onto it, it uses energy. It uses an ATP. But it's not like those regular ATP mechanisms where it's ATP plus, or ATP hydrolyzes to ADP plus PI. It actually would have been hydrolyzing, and you're going to see it in a second, to AMP plus pyrophosphate. So she's saying that instead of breaking down, usually we see, guys, usually we see ATP go into ADP plus PI, right? In this case, what she's saying is that we're going to take ATP, and instead we're going to take 2 of the phosphates off, not 1 of them. We're going to take 2 of them. You're calling it pyrophosphate. And then obviously you're left with AMP because adenomonophosphate plus PPI. That's how it works for fatty acyl-CoA synthetase, okay? Does that make sense why she did that? That's just the scheme, okay? So then the rest of it, obviously, I mean, it's just 9 FADH2, right? Plus 9 NADH. And obviously plus 9 H plus, and then plus AMP, plus PI, and then obviously plus acetyl-CoA 10 of them, right? Are we good? Does this make sense? I know this was extra, but I'm setting you up for the next one. But yeah, this one, right? Make sense? Question. If you use the acetyl-CoA for the citric acid cycle and ultimately oxidative phosphorylation, how many ATP will be produced? Show your work in order to get partial credit. Okay, I'm just gonna erase this real quickly. Did you guys know how to do beta oxidation, like multiplying and stuff?
Shouldn't the activation be -2, or is it -2?
Did I make a mistake?
I think it's -2 as well, and I thought it was -2.
She used 2 ATP for activation. I really thought it was 1 ATP. I'm genuinely not even lying. I thought it was 1 ATP because that ATP was coming from this, right? I cannot think of another place where ATP was used. It's not used in beta oxidation because you make it, obviously acetyl-CoA. You're not using it for carnitine shuttle, right? You never started with pyruvate. You're only starting with acetyl-CoA, so you never even hit the PDC complex. So I don't know where this other ATP is coming from. Citric acid cycle doesn't need ATP at all. It doesn't. Unless, nope, it does not. I'll just write it real quickly, but 1 turn of the citric acid cycle is gonna make 3 NADH, right? 3 NADH is gonna make 1 FADH2, and it's obviously gonna make 1 ATP, aka it's GTP, we just say ATP, same equivalent. So if you have 10 acetyl-CoA, you just multiply these stuff by 10, right? Obviously. Multiply by 10, multiply by 10, 10, right? This is gonna give you 30, this is gonna give you 10, and it's gonna give you 10 ATP, right? But obviously, these carriers have to go to electron transport chain, so you're gonna convert them, right? Multiply this by 2.5, because it's NADH. Multiply this by 1.5, because it is FADH2. Can somebody tell me, actually it's written right here. That's gonna give you 75, and that's gonna give you 15. Thank you very much, 15. So let's underline, okay? But we can't forget, we have these ones right here, right? So, do the same thing times 2.5, and then we're gonna multiply by 1.5. Can someone tell me what it is up there? 13.5? Okay. If you add all of this together, you're gonna get 108 ATP, 100 ATP, I can't even tell, is it 108? Yeah. It's 100 ATP. You're gonna get 100 ATP just from the citric acid cycle when you add 10 acetyl-CoA, right? Did everyone understand what I did here, right? I'm just multiplying it all out, okay? For the 9 rounds of beta oxidation, you produce NADH, step 3, and you produce FADH2 in step 1, right? So multiply these by 9, convert them into ATP with their, their units and whatever, and you get them right here, add it all up, and you eventually get 136 ATP. I genuinely think it is 135 if you use it activation, right? Activation meaning that we're gonna take that fatty acid, push it into the acetyl-CoA, and that's just right up here. Fatty acid, use ATP, fatty acetyl-CoA, subtract by 1. Are we good? Okay, let's go quickly through the next one. Oh man, I didn't even realize I did this many. Okay, this one is really easy. I mean, the answer is honestly right there too. All I did for this one is I looked at the PowerPoint for it, okay, and I found it, right? She's asking in 1 beta oxidation round, she's asking for what does it all look like? What does it look like, right? So you have to understand what's happening in each step. And a good way to do this is to understand what is beta oxidation. Beta oxidation, you're always trying to cleave the alpha carbon and the beta carbon. And you can see it right there. I kind of circled it, the alpha carbon and the beta carbon, which is up there, circled in blue, okay? You're breaking it each time by 2 carbon units, alpha, beta. So I have it signaled, I have it written out, it's in red, the acetyl-CoA group, and then the rest of the chain, starting with the beta carbon. Are we good where I am right now, right? So we're going to use the first enzyme, dehydrogenase. A dehydrogenase is basically going to take off the hydrogens, okay, and it's going to give it to FADH to make FADH2, or FAD to make FADH2. It's going to take 2 hydrogens off. The objective of step 1 is to create that double bond between alpha and beta, and that's exactly what it does. What this dehydrogenase is doing is taking off the hydrogen from carbon, the alpha carbon and the beta carbon. As soon as it takes it off, you get that double bond, right? Because it has to keep the formal charges, everything, you know, neutral essentially. So you get the carbon double bond between alpha and beta. Do you see that? It's right there. Now you use the second step, you add water, hydratase, adding water. Usually water is added by adding an OH and a hydrogen, right? Because it's H2O, easy. So you're gonna add an OH to the beta carbon, and you're always going to add a hydrogen to the alpha carbon, right? That's why you initially had 1 hydrogen and alpha carbon, which is right there in red. Ugh, you see it, right? Okay. And then what happens here is that I add another hydrogen, that's why it becomes 2 now, and I added the OH, which eliminates that double bond, right? All I'm saying is you take off the double bond, okay? After that, you use the dehydrogenase. You already saw in the beginning in step 1 what the dehydrogenase does. I'm gonna take off 2 hydrogens again. What am I gonna do? I'm gonna take the 2 hydrogens off from right here. This one and this one, the beta carbon. I'm gonna take both of the hydrogens off the beta carbon and I'm gonna collapse it to make a carbonyl. Do you know why she does this? Do you know why they do this? It's because, remember, you're trying to break carbon alpha and carbon beta. This is carbon alpha, that's carbon beta. As soon as I take off, okay, the hydrogen from here and the hydrogen from here, right, collapses and I make this double bond O with carbon. Do you remember from organic chemistry that that is electrophilic? It can get attacked, right? And you want to break beta and alpha. So you're going to take CoA, okay? What CoA is going to do is, this sulfur is nucleophilic. It's nucleophilic, it's going to attack right here, that electrophile that you just made when you took off the 2 hydrogens and gave it to NADH. Do you guys see what I'm talking about right now? Yes or no? Say yes, no.
Yeah.
Yes, you see it? Okay, cool. So I took off the 2 hydrogens, hydrogen here, got that double bond O, and those hydrogens were given to NADH. To break it now, because it becomes electrophilic, that's the whole idea. You want to make it electrophilic to break it. This sulfur in CoA is nucleophilic, it's going to attack this electrophile that you just made when you took off the hydrogens, right? And it's going to break it in half. And you see where the CoA goes? It goes, attaches right here. And I get my acetyl-CoA group that was right here. Does that make sense? I kind of showed you where all these hydrogens are coming off of, right? So from one round, you're gonna get a carbon-14 chain, right? Carbon-14, it was originally carbon-16, two more carbons, right? And those 2 carbons are gonna be in acetyl-CoA the first round. Second round, if you take 2 carbons off, it's gonna become 12 carbons. Another 2, 10, 8, 7, 6, you know, or, God, I can't, yeah, okay. Does that make sense? Yep. What you have to understand is that in the slides, she says 3 acetyl-CoA make 1 mevalonate, right? But in cholesterol biosynthesis, you technically need to also make isoprene, right? So she says to make mevalonate into an isoprene, you're gonna have to use one of them okay, to make one of them. So it's just 1 to 1, right? And then after that, you're going to use 6 isoprene to make a squalene. One thing you have to understand is that an isoprene is a 5-carbon unit. It's 5 carbon units. That's what an isoprene is. When you make a squalene, it becomes 30 carbons. That's why you use 6 isoprenes for it. That's just, you should know that it's 5 carbon unit. No, remember that isoprene is a 5 carbon unit. That you should know. And then after that, you're going to get a bunch of cholesterol or other types of products. Cholesterol either in plants, animals, things like that. So the question is asking, outline the general steps of cholesterol biosynthesis, beginning with acetyl-CoA. How many ATP and NADPH are needed? Okay, so first of all, I told you that you need 6 isoprene to make what? 1 squalene, right? 1 squalene. And I told you that to make 1 isoprene, you only need 1 mevalonate, right? The thing is, you need 6 isoprenes. So you need to use 6 mevalonate, okay? People forget that they think it's just 1 to 1 each time. It's not. You have to make a bunch of those carbons happen, okay? It doesn't just come from 1 unit of it. So you're going to start with, actually, this is kind of out of order, but it's fine. I'm going to tell you right now. First, you know that 3 acetyl-CoA make 1 mevalonate, right? 1 mevalonate makes 1 isoprene, but I need 6 isoprenes, right? Which means that I need 6 mevalonate, right? And 3 acetyl-CoA make 1 mevalonate, but I need 6 mevalonate. So, what's 3 times 6? 18. I'm gonna need 18 acetyl-CoA to make 6 mevalonate. Do you see where these numbers are coming from, right? I think it's a little bit of a basic math here. So I'm going to start with 18 acetyl-CoA are going to make 6 mevalonate, right? In one synthesis, from 3 acetyl-CoA to only 1 mevalonate, you use 2 NADPH. But right now, I made 6 mevalonate, which means that I'm going to do 2 times 6, right? Because I made 6 of them. So I'm going to use 12 NADPH. Easy, right? Is this making sense? The numbers and stuff? After I make acetyl-CoA to mevalonate, I told you that you need isoprene now. 1 mevalonate makes 1 isoprene. But we need 6 isoprenes to make that squalene in the end, right? So we're going to do 6 mevalonate make 6 isoprenes. So, right here, 6 mevalonate, 6 isoprene. In only one synthesis, it makes 3 ATP, but I need to make 6 isoprene. What's 6 times 3? 18. So you're going to use 18 ATP. Last step. I finally have the 6 isoprene, right? So it's just going to go into the squalene. There's no need to think of it any different. And to do that, it's just going to use 1 NADPH for it. So you get the squalene. The squalene is kind of like, okay, I'm not going to actually say that because that would have confused you. The squalene is like the head, kind of like, it's like the branching points. It can make lots of stuff, right? Meaning that I use a monooxygenase on squalene, and it can get me to cholesterol, or it can get me to technically other types of cholesterols, right? It's a branching point. So once squalene goes into cholesterol, you use another NADPH. So total, you're using 14 NADPH, 2 from here, 12 from here, and 18 ATP from the very first step. Are we good? I just kind of what slide it is, but this image right here, you should memorize this image no, I'm telling you, do this for yourselves. It will make you a big favor when you're doing the stuff in the future, okay? You guys know the difference between VLDL, LDL, HDL, all of that, right? Chylomicrons. Let me give you brief really quickly. Chylomicrons are usually transporting triacylglycerols, right? Just tags. Then I have VLDL. It's very low density lipoproteins. Those are just carrying some tags, some proteins, some cholesterol esters. It's just carrying here and there, okay? But then we got low LDL, low density lipoproteins. LDL, guys, is really bad for you because if you eat a lot of fatty like diets and stuff like that, you're gonna generate all that cholesterol because LDL primarily carries cholesterol. That's why it's called low density lipoprotein. It's not that dense because it's carrying so much cholesterol, right? It's not high density, okay? It's low density. Low density is gonna accumulate on your blood vessels. As it's accumulating on your blood vessels, what's happening here is you're basically blocking those blood vessels from having blood going through, right? You get CVD, cardiovascular disease and stuff. But then, we're able to actually fix that. Some individuals have high HDL. Actually, my mom has a high HDL, but the doctor told her it was bad. I have no idea why. They said she had too much HDL in her. I don't know, whatever. I guess too much of anything's bad. But what HDL is gonna do is that it's gonna take off that LDL that's building up in the walls, right? Let's erase this real quickly. Okay, I'll show you. What's happening here is that if this is my blood vessel, right? This is all the LDL that's basically accumulating, right? What's gonna happen here is that now I have this thing called HDL, high density lipoproteins. When we say high density, we're saying it has lots of protein, HDL, right? It doesn't have a lot of cholesterol, it has a lot of protein. Those proteins are what take off this cholesterol, that LDL that's accumulating on the blood vessel. So what's gonna happen here is we're gonna have this HDL come in, boom, 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 whatever. It's gonna come in and it's gonna take off the LDL. It's gonna take off that cholesterol through a mechanism called LCAT. It's gonna use the mechanism LCAT, take off the cholesterol, and it's gonna bring it actually back into your liver. And your liver can process whatever it wants to do with it. It's actually on the top right here. It goes through a LDL receptor. You can see the cholesterol can go into the bile salts pathway, because it's right up there. Or it can go into cholesterol esters, make VLDL, and do the same process again. Do we see what we're saying? The cholesterol that isn't put into your adrenal glands, muscle, and adipose. The problem with that is that, again, people who eat too much of fatty diets, okay, it's accumulating to the point where it's not even going here anymore because those storages are already filled up with that cholesterol. Instead, what's happening here is that it's getting sent out, becoming macrophages, foam cells. We're seeing it on the blood vessels. That's an issue. We take the HDL, we're going to take it off, okay? You don't want too much of anything. So that was my whole spiel with that. Let's see something. So just to answer this very, very last question. Cholesterol ester, okay. I think I just, let's talk about it just real quickly. So cholesterol ester, basically how does it work, right? How is it packaged and sent to other tissues? Cholesterol is packaged, right, into LDL, low density lipoproteins. That's what we said, right? That's the carrier for it. And what's happening here is that that's going to be sent through the bloodstream. LDL, right? Remember we said chylomicrons are in tags, right? They're in tags because they're not water soluble. They have to be in something that can transport it. That's the same idea with cholesterol. You're putting in an LDL instead. So LDL is going to go through the bloodstream, okay? And as it goes through the bloodstream, what's going to happen here is that it's going to go into target areas and organs. We're talking about adrenal glands, we're talking about adipose tissue, we're talking about even the heart, right? Because the heart works off of fatty acid oxidation, okay? And I know we're not talking about fatty acids right now, it's cholesterol. Same idea with the idea that they're fats. So, and hydrophobic. So what's happening here is that as soon as we get these cholesterols, they're at the target, they're going to do receptor-mediated endocytosis. What I'm saying here is that basically, if this is my organ, right? This is my fat, this is my cholesterol, LDL basically, right? What's going to happen here is that there's going to be receptors right here, receptors. As soon as this comes near it, it's going to open up like that, and it's going to take it in, and then finally, it's going to engulf it, right? And it's going to look like that. That's receptor-mediated endocytosis. It sees a receptor, it's going to bring it inside. So, that's it. But obviously, you got to package it into VLDL first to get it into the bloodstream, okay? Are we okay with that, right? I feel like it's redundant for me to just continue on and on and on. Get your cholesterol, it's inside the liver, it gets processed as VLDL, gets sent out of the liver. After that, I'm gonna have a IDL, intermediate density lipoproteins. What do you think that is? Honestly, it's what it says it is. It's intermediate, meaning it has some cholesterol, has some tags, has some free fatty acids. Then after that, once you've gotten rid of the tag, We've gotten rid of the free fatty acids, and there's only cholesterol left. We call that LDL. That LDL, however much you have of it, is gonna go then to those adrenal glands, to the mammillary glands, to all those glands. Anything that is excess is gonna build up on your blood vessel walls. Are we good now? That's all I have today. Okay. I would really recommend memorizing this picture though, so, yeah, call it a day. Thank you guys.